Okay, so good morning. Today we will discuss chapter 4. So, under Enforced Concrete Design. So, the seismic design and detailing of special moment frame members. So, quick or brief introduction about detailing of special moment frame members. So, why do we need to detail or have an additional special detailing provision for enforced concrete building? Okay, so as we all know, we were located in seismic zone 4. So the probability of having bigger earthquake here is higher. So but aren't section 401 to 417 of NSCP and section 419 to 426 enough to keep our building earthquake resistant? So the answer partly lies in understanding the main difference between the strong and being tough. So being strong versus being tough. Okay. So recall that we learned in our material science subject that some metals or some materials are observed to be strong. So that is a definition of strong is they can support or withstand extremely large loads. But if this material are brittle, so they may be exhibit signs with distress or even failure when they are subjected to lesser loads, but which are applied quickly and repeatedly. So in comparison with the materials that observed to be tough, so that is they can support or withstand large loads, or they can capable withstanding frequent and cyclical or repetitive application of loads, and they can or they are capable of energy dissipation. So being a strong, okay, or designed strong is not enough. Okay, so our building or our structure should be or must be tough. Okay, so they are also considered ductile. Meaning of ductile is they are capable of undergoing large deformation with little loss in their ability to support the imposed loads. So that is why our code need or our code tell us to have our special moment resisting frame members that subjected to earthquake should exhibit ductile behavior and should have absorptive capacity to sustain large deformation. So section 418 provides us design and detailing to enhance ductility requirements that are intended to resist strong earthquake ground motions without significant loss of stiffness and strength. So let's go to the detailing and design of beam of a special moment frame. So this is under NSAP 2015 section 418.6. So in this section provides designs and detailing requirement of beam, SMRF beams, lateral loads induced by earthquake ground motions and proportion primarily to resist flexure and shear. So beams of special moment resisting frames shall satisfy section 418.7. So as provided in the section, dimensional limits and minimum detailing requirements of longitudinal and transverse reinforcement shall be satisfied. So first, for beam detailing, so there is a what we call a dimensional limit. So under 418.6.2.1, so beams shall satisfy A through D. So it says clear span LN, okay, from face of the column up to the face to face of the column shall be at least 4D. 4D is the effective depth of the beam. Okay, so letter B. Okay, with BW shall be at least 0.3 of H. Okay, so H, and then with BW shall be at least 250. Ayan. Okay, so at least 250 millimeter, and then the ratio of B over H is must be greater than or equal 0.3. And then the projection of the beam with beyond the width of supporting column on each side shall not exceed the smaller of C2 or 0.75 CT, or smaller between C2 or 0.75. So you can have a beam that is wider than your column, okay, but the code's requirement, so when we project, so this is your beam, okay? So this is your beam, and this is your column. Okay, so when we project 45 degrees the beam to column, the sides or the measurement from the face of the column of your beam is not greater than the smaller of C2 and 0.75 of C1. So C2 is the smaller dimension of, okay, so C2 is smaller dimension of your column, then C1 is the larger or larger dimension of your column. Okay, so you need to compare that to, okay, so you can now you can get your BW, okay, or the total width of your beam. Okay, so for longitudinal requirement, so have at least 2 continuous bars at the top and bottom faces. So at any section, for top as well as for bottom reinforcement, the amount of reinforcement shall be at least that required by section 409.6.1.2, where A is mean. Okay, then the greatest between this 3, no? So the first one is square root of FC prime, okay, over Fy over 4 BWD. Okay, so our AS should be greater than or equal to the AS mean. So AS mean, yan. So, and AS is greater than or equal AS mean equals to this one. So 1.4 Fy over Fy BWD, and then AS, okay, should be greater than or equal, so the required in the analysis. And also the reinforcement ratio rho or AS rho shall not exceed 0.025. Okay, so rho is equal to AS over BWD. So AS should be less than or equal sa 0.025 BWD. And then for 18.6.3.2, so positive moment strength at joint face shall be at least 1/2, and the negative moment strength provided at the face of the joint, and then both negative and positive moment strength at any section along member length shall be at least 1/4, okay, 1/4 naman of the maximum moment strength provided at the face of either joint. So note that AS minimum, our AS minimum need not be satisfied if AS supplied is 1/3 greater than AS required. Okay, so need not be satisfied if our AS supplied is already 1/3 greater than AS required. Okay. The next, the positive moment strength at joint face shall be at least 1/2, and the negative moment strength provided at the face of the joint, both the negative and the positive moment strength at any section along member shall be at least 1/4 of the maximum moment strength provided at the face of the joint. So this is the illustration of the codes detailing on the reinforcement of beam. Okay, as you can see from your point of this deflection, ito, okay, so transition of positive and negative moment. So our AST here, the top of the top of the beam. Okay, so as you can see, it is must be greater than the required from analysis, or equal or equivalent to 2 bars. So, or 1.4 over Fy BWD, or square root of Fc prime over 4 Fy BWD, and it does not exceed the 0.025 rho. Okay, so AST must be less than or equal 0.025 BWD. And then for your bottom bar or compression bar here. Okay, so our AS our area of steel is or should be greater than or must be greater than the required for or equal from the required of from analysis, and then the equivalent of 2 bars, then must be greater than with these two terms, okay, or equation. And then you need to compare your bottom bar to your also to your AS at your top, okay, or AS top. So AS top or AS bottom must be greater than or equal AS top divided by 2. So after the point of inflection here, so we have here the LD, okay, so developmental length. Okay, so you need to protrude your beams here, top and bottom, with at least, okay, the D dimension, okay, D dimension, whichever is larger, D dimension or 12 the diameter of the bar, or L over 16. So L is the face from face to face of the column. Okay, so that is for the length, okay, or developmental length. And then the number of for rebar, okay, so at least, okay, 1/3 of AST. And then from that point, our point of inflection, our A max or AST max is, or A max should be less than or greater than or equal A max over 4. So yan. And then this one. Okay, so lap splices of the form longitudinal reinforcement shall be permitted if hoops or spiral reinforcement is provided over the lap. Spacing of transverse reinforcement enclosing the lap splice bars shall not exceed D over 4 or 100 mm. Okay, so when you have lap splices or joints between your bars, the transverse or hoop or spiral should be smaller between D over 4 or 100 mm. So also, lap splices shall not be used in location from A to C. Okay, so first one, bawal daw maglagay ng lap splices sa joints. Yan. Then within a distance twice the beam depth, okay, from the face of the joint. So example, this is your joint. Yan, bawal dito yung splicing. Then bawal sa distance twice the beam depth. So the beam depth is H. So bawal din dito. And then within the distance of the twice of the beam depth from the critical section where flexural yielding is likely occur. So as a result of lateral displacement beyond elastic range region. Okay. So the next one is transverse reinforcement for beam. Okay. So based on 418.6.4.1, so hoops shall be provided in the following regions of the beam. So over a length equal twice the beam depth measured from the face of the supporting column toward the midspan, okay, at both ends of the beam. So next one is over the length equal to twice of the beam depth on the both sides of a section where flexural yielding is likely to occur because of lateral displacement beyond the elastic range behavior. Then where hoops are required, primarily longitudinal reinforcement bars closest to the tension and compression phases shall have support in accordance of the designing of shear reinforcement under section 425.7.2.3 and also 425.7.2.4. The spacing of transversely supported flexural reinforcing bars shall not exceed 350 mm. And then skin reinforcement required by section. Okay, this section need not be laterally supported. Okay, for our hooks. Okay, so hoops need the beams shall be permitted to be made up two pieces of reinforcement, a stirrup having a seismic hook at both ends and closed by cross tie. Consecutive cross ties engaging the same longitudinal bar shall have their 90-degree hoops or hooks, but the ACI code tells us to have 135 degree hoops for our cross ties and hooks. And then for 118.6.4, okay, so the first hoop be located not more than 50 mm, okay, from the face of the supporting column. And then the spacing of hoops shall not exceed the smallest of A through, okay, C. So as you can see in this illustration, so the first hoop or the first, okay, stirrups, okay, from the face of the column should be 50 mm. Okay, so after 50 mm, it should the spacing of the hoops shall not exceed the smallest of these following. Okay, so D over 4, okay, effective depth over 4, then 6 times the diameter of the smallest primary flexural reinforcing bars, excluding longitudinal skin reinforcement, so by section 409.7.2.3, and also dapat hindi lalagpas sa 150 mm yung spacing. So where hoops are required, they shall be designed to resist shear according to 418.6.5. Okay, and then where hoops are not required, so transverse reinforcement, that is VST is not required. Okay, so stirrups with seismic hooks at both ends shall be spaced at the distance not more than D over 2. Okay, so this is the maximum spacing, okay, for a region that seismic hooks is not required. So in beams having factored axial compressive force exceeding AG FC prime over 10, hoops satisfying section 418.7.5.2 through 418.7.5.4 shall provide a long length given in this section, 418.6.4.1. So along the remaining length, hoop satisfying section 418.7.5.2 shall have spacing of S not exceeding smaller of 6 times the diameter, okay, of the main smallest longitudinal beam bars, or 150. Yeah. So same lang din. So where concrete cover or transverse reinforcement exceeds 100 mm, then additional transverse reinforcement having not exceeding 100 mm and spacing not exceeding 300 mm shall be provided. Okay. So the detailing of your hooks here. Yan. The extension of your rebar, okay, hook should be 6 dB or not greater than 3 inches. Okay. For cross ties, so ganda naman. Same lang. 6 dB. Okay. So maximum spacing between, okay, so bars restrained by legs of cross ties and hoops is 14 inches. Okay, so design shear force, so VE. So section 418.6.5. So the design shear force VE shall be calculated from the consideration of the forces on portion of the beam between faces of the joints. So it shall be assumed that the moment opposite sign corresponding to the probable flexural strength MPR act at the joint of faces, and the beam is loaded with the factor tributary gravity load. And then yan, transverse reinforcement over length identified in the section 418.6.4.1 shall be designed to resist shear, assuming VC or shear for concrete is equal to 0 when both A and B occur. So first, the resistance of the earthquake induced shear force calculated in accordance to 418.6.5.1 represent at least one half of the maximum required shear strength within those lengths. Then the second one is the factor, the PU should be less than or equal AG FC prime over 20. Okay. So it says here that the one half of your VE is equal to maximum shear strength within those length. Okay, so from your analysis, okay, and so the MPR here is equal to the or the shear there is equal to the MPR at A or 1, and then MPR at 2 over plus MPR 2 or at 0.2, and then divided by your LN. So it should be less than, or one half of VE should be less than MPR 1 plus MPR 2 divided by LN. So simple mechanics. Okay, and then additional notes from ACI 318-14. So the VE, okay, the initial the VE is equal to okay, the VE here at this portion when the load is subjected, or the beam is subjected to gravity loads WU. So it is equal to the MPR plus MPR 2 divided by LN, then plus or minus WLN over 2. Okay, so the end moments MPR based on steel tensile stress of 1.25 Fy, where Fy specified the yield strength. So both end moments should be considered in both direction, clockwise and counterclockwise. Then end moments MCR for columns need not greater than moments generated from or by the MPR of the beams framing into the beam column joints. So VE should not be less than that required by the analysis of the structure. So the probable moment MPR is determined using the properties of the member joints, faces assuming a tensile strength in the longitudinal at least 1.25 Fy, and the strength reduction factor phi is 1.0. So this should be your equation for your probable moment MPR. So it is equal to phi, okay, which is 1.0. So A multiplied by AS, then at least 1.25 Fy, then multiplied by D minus A over 2. So the design shear force V is actually the sum of the shear from plastic end moments plus the gravity shear. So this one. Okay. So now let's go to a column of special moment frames. So 418.7.2. So dimensional limits, column shall satisfy A and B. Okay, so the shortest cross-sectional section should be at least 300 millimeter. Okay, and then the ratio of the shortest cross-sectional dimension is to the perpendicular dimension shall be at least 0.4. So in short, B over H is greater than or equal 0.4. So for the minimum flexural strength of column for 18.7.3, so columns shall satisfy section 418.7.3.2, then or 418.7.3.2. So from your analysis, okay, so as you can see, this is the moment interaction, actual moment interaction diagram or column interaction diagram. So you can use this to design your minimum flexural strength in columns. Okay, so the flexural strength of column shall satisfy also. So the summation of nominal flexural strength of column must be greater than or equal to 6 over 5 the summation of nominal flexural strength of the beam in framing into the joints, no? So the code tells us to have a strong column, weak beam connection. Okay. Then for longitudinal reinforcement, so area of longitudinal reinforcement AST shall be at least 1% of AG. So in between 1% of AG, okay, and okay, shall not exceed 0. or 6% of your AG or area gross. Okay, so in columns with circular hoops, there shall be at least 6 longitudinal bar. Para naman sa rectangular or square hoops, so 4, okay, longitudinal bars. Okay, so same with our beam. So transverse reinforcement, so based on NSAP section 418.7.5, okay, so transverse reinforcement required in section 418.7.5.2 through 418.7.5.4 shall be provided over LO. Okay, so LO should be greater than or equal to H over 2, H over 6, and then 450 mm. So H over 2 is the depth of the column at the joint of the joint face at the section where flexural yielding is likely to occur. And then yung H over 6, yan, yung 1/6 of the clear span of the column. And then 450 mm. Okay? So pipili ka dun sa tatlo, sino yung pinaka malaki dito sa tatlong yun yung gagawin mo LO. Ito yung LO. So distance between the it is from the face of the face of the beam, okay, at up to this point. Okay. Okay, so for your spacing, okay, for your spacing, so for your spacing, so the first spacing for your transverse bar should be S over 2. Yeah. Okay, so S is equal to or must be from the spacing of the under LO, okay, section or LO zone should be less than or equal H1 over 4, okay, the depth of the column, okay, over 4, or less than or equal 100 mm. Okay, and then beyond the LO, okay, so your spacing should be, okay, less than or equal 6 diameter of the bar or 150. Okay, whichever is smaller. Okay. So transverse reinforcement shall be in accordance with A through F. A transverse reinforcement shall comprise either single or overlapping spiral hoops, circular hoops, or rectangular hoops with or without cross ties. So bends of rectilinear hoops and cross ties shall engage peripheral longitudinal reinforcing bars. So cross ties of the same or smaller bar size as the hoops shall be permitted subject to limitation of section 425.7.2.2. So consecutive cross ties shall be alternated and for end along the longitudinal reinforcement around the perimeter of the cross section. So alternating. And then where the rectilinear hoops or cross ties are used, they shall be provide lateral support to longitudinal reinforcement in accordance with section 425.7.2.2 and then up to 425.7.2.2. And then reinforcement shall be arranged such that spacing xi of longitudinal bars laterally supported by the corner of the cross tie of hoop leg shall not exceed 350 mm around the perimeter of the column. Okay. Yeah. So later, discuss natin yan. And then where PU is greater than 0.3 of AGFC prime and FC prime is greater than 70 MPa in columns with rectilinear hoops or square or rectangular column, every longitudinal bar or bundle bars around the perimeter of the column concrete core shall have lateral support provided by the corner of the hoops or by seismic hook, and the value of xi shall not exceed 200 mm. So PU shall be the largest value in the compression consistent with factored load combination including E. Okay, for spacing naman of transverse reinforcement, it should be not exceed the smallest of from A to through C. So the first one is the H over 4, okay, 1/4 of the minimum column dimension, and then 6 times of the diameter of the smallest longitudinal bar. So same with this. Okay. Or SO should can be calculated, okay, as SO is equal to 100 plus 350 minus HX, okay, so over 3, or where S, okay, or spacing is in between 100 and 150. So for the amount of transverse reinforcement shall be in accordance with the table 418.7.5.12. Okay, the concrete strength factor Kf and confinement effective factor Kn are calculated by the following formula. So where Ni is the number of longitudinal bars or bar bundles around the perimeter of the column core with rectilinear hoops that are laterally supported by corner hoops or seismic hooks. So transverse reinforcement for column of special moment frames. So this table is for transverse reinforcement. Say for transverse reinforcement, so you need to calculate the ties or transverse reinforcement over the following condition. So when PU is less than or equal to 0.3 AGFC prime and FC prime is less than or equal to 70 MPa, so the applicable expression, so you need to calculate A and B, which is greater between A and B alone. Okay, so this one. Then when this one is your condition, okay, okay, so it says here that PU less than or equal to 0.3 AGFC prime or FC prime is less than or equal 70 MPa. So you need to get the greatest between the three expressions. So same with the spiral hoops. Okay. So here is the illustration of your detailing for column. Okay, so the dimension xi is from the center to center line of laterally supported longitudinal bars. It should not exceed 14 inches or equivalent to almost 350 millimeters. Then the term hx, okay, used in equation 5.3 is taken as the largest value of xi. Okay, so yeah, xi should be the outer, okay, should be the outer to outer distance of your ties or transverse reinforcement. So again, your extension here 6 dB or not less than 3 inches. Okay, and then the cross ties engaging, okay, the same longitudinal bars have 90-degree hooks on opposite side. Okay, so alternating siya. So this is your first hook. Then kapag meron ka naman sa isa, dito naman. Okay. So transverse reinforcement, okay, so VE, okay, so the design shear force VE shall be calculated from considering the maximum forces that can be generated at the face of the joints. So this is your VE computed for column. Okay, so VE is equal to MP3 or moment at the end of the summation of moment at the end of the column divided by the clear span or LU. Okay, clear height. Okay. So transverse reinforcement are LO over the length LO, okay, in section 418.7.5.1. So to be shall be designed to resist shear assuming VO is equal to 0. Almost same lang yun din sa ating beam, no? Beam requirement. Okay, so over 20 and then at least 1/2 of the maximum shear required shear of LO. Okay, so for joints of special moment frames, so forces in longitudinal beams, reinforcement at the joint face shall be calculated assuming that the stress in the flexural tensile reinforcement is 1.25 Fy. A joint transverse reinforcement, yan. So forces in longitudinal beam shall satisfy this following section except as permitted by this section. So where beam frames into four sides of joints, where each beam width is at least 3/4 of the column width, the amount of the reinforcement required is under 418.7.5.4. So babalik ka lang dun sa requirement dun sa column natin. Okay, so and then this is the shear strength of joints natin, nominal joint shear strength. So Vn. So transverse reinforcement for joints combined beams, all four sides, no, or all four faces. So ito yung ating Vn. And then for our joints confined by only three faces or two opposite faces, so ito na yung computation mo. And then for other cases, ito naman. So refer to section 418.4.2. So for this one, and then yung lambda natin is equal to 1.0 pag normal weight, and then 0.75 naman kapag lightweight concrete. So AG natin dito is given in section 418.8.4.3. So yan. Yan ang table 418.8.4.1. A joint is considered to be confined by a beam if the beam width is at least 3/4 of the effective joint. Okay, width. So extension of beams at least 1 overall beam depth h beyond the joint face are considered adequate for confining that joint face. And then effective cross-section area, AJ, yung kanina. So this one. So this one is your AJ. Effective joint area. Okay. So effective joint area shall be or shall not exceed lesser of these two. Okay. So beam width of plus joint depth, then twice the smaller of the perpendicular distance from the longitudinal axis of the beam to column side. Okay. So this one. Okay. So it should not lesser between beam width okay plus 2x or plus joint of the depth, and then twice of the smaller between the distance of the column side. Okay. So you can now get AJ by using by multiplying h or joint depth in the plane. Okay, so joint depth. Okay, and then the effective joint width, B plus h, or it must be not or equal to not less than or equal to B plus 2x. Okay, so that is the end of our detailing. We will now proceed to a sample problem for seismic design detailing of SRM. So thank you. So bye.